Hello everyone. Good afternoon, ma'am. Good afternoon, Dr. Shima, ma'am.
Good afternoon, ma'am. Good afternoon.
Good afternoon, Dr. Devi Kala, ma'am. Good afternoon, sir. Venkatesh, sir. Ma'am, shall we start the program, ma'am?
Yes, ma'am.
Yes. Shall we wait for
Just
5 more minutes? Shall we wait, ma'am?
Yeah, ma'am, no problem.
yeah, we can wait for 5 more minutes, ma'am.
Yes,
If
ma'am.
the participants will join.
Yes.
Yeah.
Okay.
Usha, ma'am?
Yes, ma'am.
Yeah, I think we can start, ma'am.
Okay.
Start the
Okay,
session.
ma'am. Yes,
Ma'am,
ma'am.
Yeah,
Doctor,
yeah,
ma'am?
yeah.
Dr.
I will.
Seema, ma'am?
Yes.
Okay, ma'am.
Yes. A warm and pleasant good afternoon to everyone. We are so glad to meet you all for the third day of the Faculty Development Program on cryptography and its applications, conducted by Mohamed Sathak AJ College of Engineering, Chennai, in collaboration with MIT Square, London. I extend my sincere thanks to the management, faculty members, participants who help us to lead this program successfully. Cryptography in general shifts the balance of power from those with the monopoly on violence to those who comprehend mathematics and security design. Dear participants, I hope this FDP will surely help the faculty members with the knowledge and resources to integrate cryptography concepts into their teaching curriculum and enhance the quality and relevance of their courses and also for researchers. I extend a most cordial welcome to our speaker, Dr. Shima Ramesh Maniyat, Assistant Professor, MBJ College of Engineering, Bangalore, for her presentation on today's topic, DNA coding scheme with a hybrid encryption algorithm using SPM technology.
Thank you, ma'am.
Yes, ma'am. Over to you, ma'am.
Yeah,
Please, ma'am.
yeah. Thank you. Good afternoon, one and all present here. So today, for the day 3 of FTP, I would like to share one of my work on DNA coding scheme with hybrid encryption algorithm using a support vector machine. So this is my today's agenda. I'll be talking about the introduction and literature survey, objective of research, the proposed design flow, the conclusion, and the reference. So before starting this one, so I just want to tell about supervised learning algorithm, or SVM, or support vector machine. Okay, it's a type of supervised learning algorithm mainly used in machine learning, right, to solve the classification and regression tasks. So here I'm not doing any classification. Okay, I'm just what I've done is to get the secret key. I am training the SVM, support vector machine, with the input image as a input, and the target is my encoded image. So with this I'm training, and the trained value what I got is I'm used as a secret key. So this is the main intention of this work. Okay, so I'm not doing any major classification because that confusion will come always. SVM, support vector machine, is a type of supervised learning, and it can be used mainly for classification regression tasks. So that I'm not doing here. To get the secret key, I have taken the help of SVM. Okay, and I got the trained value. The trained value is my secret key here, which can be used for encryption. Fine. So in every encryption method that as today already discussed, we are using confusion diffusion method. So confusion is literally just we are scrambling it, just we are confusing the pixels, and diffusion means we are doing bit XOR. So that in diffusion we are changing the pixel value itself. Confusing means just we are rearranging, just shuffling it, right? So this also here also I'm following the same method here, both principles, and also the evaluation metrics. For every encryption algorithm, we have to make sure our algorithm is showing, or is that has undergone all the evaluation metrics. What are the evaluation metrics we have to show here? Mainly correlation analysis, then information analysis is there, then we have to show histogram, NPCR, structural similarity, etc. So in anti-statistical attack capability, I have shown cryptography, the correlation analysis with horizontal, vertical, and diagonal correlation analysis have shown here. And similarly, entropy, we have to get entropy value near to 8, close to 8 we have to get. And NPCR, we have to get near to 100%. UACA for 33% is for a good encryption algorithm. Okay, and it can be less than 9, it can be 80 also. NPCR, even UAC, it can be less than 50%, but that shows how strong your algorithm is. and SSIM, structural similarity, as I told, mainly will tell the similarity between the decrypted image, right, as well as original image. So original image and decrypted image should be similar, right? So if it is similar, means your SSIM should be approximately equal to 1. If it is not at all similar, it should be less than 1. It can be near to 0 also. So in the method, okay, the DNA coding scheme with hybrid encryption algorithm using SVM. So what I have used is DNA cryptography, because in many of my work, you can say I have used DNA cryptography. Why? Because DNA, as we know, it is a unique thing present in our human body, right? So I have used this unique thing as a secret key, DNA. So my DNA, like my sequence, I only generated. So I know my DNA secret key. So it will be different for different people, right? So that is the reason DNA I have chosen as one of the algorithm in many of my cryptographic work. Okay. So in this method, secure DNA cryptography scheme based on DNA technologies proposed here. But here I have used different coding technologies. As last day we have discussed about DNA coding technology, right? We can have 8 type of DNA mapping rule. So in that, out of 8, you can use any of the mapping rules, which will be known to only the sender or the people who is doing this encryption, right? It is not known to everyone. So that is one of the secrecy behind this. Second things, like in support SVM, support vector machine based encryption scheme has been used here along with the DNA cryptography. That is the reason I'm calling as hybrid encryption. So combination of both DNA as well as SVM. Okay, and here I have used blockwise image encryption technique that has been used in the proposed. So blockwise also we discussed in the day 1 and even day 2. I have taken the image into 4 blocks. So last time Manikandan sir was asking why can't we go for 8 block or 16? We can go for 8 block or 16 block. Okay, but here I have taken 4. So I have taken a symmetric image. Symmetric image means image of size to n cross n or m cross m. 56 cross 56 I have taken, and I have divided into 4 blocks. In each block, I have done the encryption. I have applied the encryption algorithm, and after that, I have done the evaluation metrics for various attacks. This is a for my proposed method. Okay, so here this pictorial representation will clearly explains how the work have done this. Okay, so here I can tell you one step by step. This is the first method I have chosen, that is an conventional encryption method. Okay, so here 2 methods. One is conventional encryption method that will called as level encryption, and you have level 2 encryption. So in level 1 encryption, conventional encryption method, what I have done is suppose it's my original image. Have undergone for first level of encryption. Okay, as I told, hybrid we are using. Okay, first level, second level. Okay, so first level is of encryption with the help of one DNA sequence. So DNA sequence have randomly generated one DNA sequence with the help of ACTG, that is adenine, thymine, cytosine, and guanine. So that DNA sequence randomly generated with the size same as that of my original image. For example, original image size is 256 cross 256 means I have generated a DNA sequence or DNA matrix of size same as original image. Okay, so that is DNA sequence 1, which is a secret key for first level of encryption, and that second level of encryption. In second level of encryption, another DNA sequence, because I can generate n number of DNA sequence by using my the nitrogen bases, that is ATCG, right? So second DNA sequence I have generated randomly, that is used for second level of encryption. So this is that final output is my encrypted image of first conventional encryption method. Okay, now next method is taken the same input image. Okay, so that I have just show the histogram, because histogram of the input image should be always like this, right? It should not be a uniform. Uniform will come in the case of encrypted image. So suppose this is a histogram output of the input image. So what is histogram? Histogram, it gives a graphical representation of number of pixel versus the pixel value, right? How many pixels are coming? For example, how many 250 is a pixel value, how many pixels are coming here? How many pixels of pixel value of 2 is coming here? So number of pixel versus the pixel value. So now this same image, okay, has given as an input to the SVM model. Okay, because SVM model needs some training. So to train this, I have given this input as the original image as an input. Okay, and another input is 0 to 255 array of pixels. Why is 0 to 255 in the sense? Because we know that every age the pixel value range from 0 to 255. So I have generated a random array of 0 to 55. Okay, that I have given as an input to SVM for training. So SVM training, we need a weight and a bias. So weight and bias is my another secret key, so that we can decide. That is not to me only, right? Only I know what is the weight and bias I have used for SVM training. So here we are using multiple secret key, okay, to make my algorithm more authenticated. So SVM training, we need input, that is was one input from the conventional encryption. So this encrypted image I am giving as to SVM, okay, for training. Along with that 0 to 255 array, pixel array for giving as a input for SVM training. And with the help of weight and bias, another secret key, okay, I am training my SVM, okay, and finally I'm getting an SVM model. So SVM model, okay, will give a set of values. Okay, so with the help of that values, okay, I have done the SVM encryption. So I'll the following slide, I'll tell you what SVM model I got. Okay, and what with that how I have undergone the SVM encryption. Okay, and finally we have to go with what the performance analysis. So this is the entire proposed method. Okay, so with we have to do conventional followed by SVM training. So to do SVM training, we need conventional encryption as an input. This is my this input I have taken here, and the same 0 to 55 array of pixels I have given for SVM training with the help of weight and bias. Finally, I got the SVM model. The SVM model will help for final SVM encryption. Okay, so level 1 encryption here, just only we discussed your level 1 encryption and level 2 encryption here. Okay, level 1. What is level 1, level 2? We are going to see the next slide now. So what is level 1 encryption? In level 1 encryptions, I have taken my Lena image. Okay, as I told, block-wise division I have done. Block 1, block 2, block 3, block 4. Okay, 4 block have divided. Now, here the secret key, okay, have taken as B1, B2, B3. Okay, B4. What is B1? B1 is my DNA matrix with the help of ACTG. So randomly I generated a DNA matrix. That same DNA matrix, I am taken the transpose, D transpose, I'll get B2. Okay, now B3 is rotating D twice. Rotating this D matrix twice. Okay, and B4 is D plus D transpose by 2. Just like this, we can do in different ways. If you want, you can do here you can do bit XOR, or here you can flip by like last method I have taken the flipping of D, flipped by 90 degree, flipped by. So that's how we can make how much possible, like you can make it complicated your key, that is in our hand only. This is a method I have chosen. We can do in different way also. So after this, each block is bit XOR. How we have bit XOR here? For example, here have the bit XOR have done with the help of one secret key. So the secret key is 00011011. Like in this way, I have done. If my input secret key is 00, okay, or input is 00, I should do the bit XOR of my Q1 with B1. This is my B1. Okay, Q1 with B1 bit XOR. When 01 means bit XOR of Q2 with B2. 10 means Q3 and B3. So and 11 means, so all the blocks have done the bit XOR. Okay, have done. And finally, so you can see a blockwise encryption done. So after appending all the block, I am getting a encrypted image or level 1 encrypted image like this. Okay, this I have done again permutation of, because this is like here also we can see it is not evenly distributed, right? It is here some part encrypted here like this. So I have to make it get a proper encryption image. I have done the permutation of this just scrambling of this the above encrypted image. Okay, with another secret key. So this scrambling, we can do Arnold scrambling, which already discussed, or we have different types of scrambling method, so that we can adopt here. Here I have used Arnold scrambling only. This we are shuffling here and there with the help of secret key. Okay, so here I have shown the histogram of both input image and after level and encryption. What is histogram? But here level and encryption is not that much okay, because you can see it is not that much uniformly distributed, right? So normally straight. So that is the reason I have gone for second level 1 and level 2. So in level 2 encryption, what you have to do means the output of the level 1 has to be scrambled first. So this scrambled output, this all are the result actually I got. Okay, scrambled output. Then this has to be bit XOR with K1. So again K1, K2, K3. Here I have taken in this way DNA matrix only, transpose rotating twice 90 degree and D plus D transpose by 2. Here the last previous work, what I have shown that I used here, K1, suppose this is my DNA matrix 1, K2 is just the transpose of that one, and K3 is flipped. I have just flipped this by 90 degree. So here one will come here, that one is coming here, just flipped it by 90 degree. Okay, so generate K1, K2, K3, and first after scrambling of level 1, K1 is bit XOR with scrambled image, we will get this image, and this is bit XOR with K2, you will get this result, and this is bit XOR with K3, you will get this. So this is my second level of encrypted image. Okay, so like that we have done two level one. That is, this is coming under conventional encryption method. After this, okay, we are using SVM. Okay, the SVM is used for image encryption. So as I told, we need to train my SVM, I need some input and target, right? So training array of pixels. So I have to generate a 0 to 155, 0 to 255 array of pixels. Okay, because a pixel range from 0, we have 0 to 55. That is the reason I have taken randomly 0 to 55 array of pixels. And that has to be, okay, done encrypt using level 1 and level 2 using DNA. Okay, then you'll get the encrypted image. So whatever that array of pixel I have given to the level 1 and level 2. So level 1, level 2 already explained here what is level 1, level 2. So this level 1, level 2 encryption method has done for the 0 to 55 array of pixels. So that is my encrypted image first. Okay, now here second for training, input is 0 to 155 array of pixels, and target, what is my target? This is my target. This encrypted image is my target. This target I have given here for SVM. So SVM need an input and target. With this input and target, we have done the SVM training, and these are the SVM parameters. Okay, parameters we got. These parameters will change according to your input and the target. So therefore, for different algorithm, parameters will be different. Okay, so these are the parameters which I got here. And finally, this will help, or this SVM parameters will generate a model known as SVM model, which can be used for encrypting our final input image. Okay, so here this is what SVM encryption I have done here. So input image, okay, is input image, okay, what we need to encrypt is given to or SVM, the trained SVM model. The trained SVM model we got after giving input and target. Input is my 0 to 55 pixel, target is my encrypted image after undergoing a level 1, level 2 twice. So hybrid encryption we had the different DNA key, secret key, right? So this trained SVM model, okay, will give you a set of values. Okay, that is considered as my pixel value. After training, what I got is my pixel value. So I got 0, the location from 0, 1 to 255. 0 to 55 is my input I have trained, given for trained. Right? So I will be getting for every 0 to 255 locations, I have got a different values. These are my trained pixel values. Okay, so what is the XVM encryption actually here? So suppose this is my input image. The input image is having size 256 cross 256, right? This is a pixel image. Okay, so in this image pixel values I have plotted here just for example to understand the pixel value of my input image. Okay, each pixel value of input image I'm replacing with this trained SVM value, like I'm doing 1-to-1 mapping. So for example, this 1 is replaced by 38, 0 is replaced by 25. So I am getting a new encrypted image because this is my original pixel value of my Lana image, right? This is replaced by the SVM train values. How we get SVM train value? SVM train value we got after doing level 1, level 2 encryption, okay, with the help of weight and bias, right? So that is my final encrypted image. So I'm getting a exactly uniform histogram for my output SVM encrypted image. Okay, then finally I have to go for performance analysis. This is what I have done the SVM encryption method. So in the previous method also I have shown all this calculation. So here also I have taken test images Lana of size 56 or 56, and this is a proposed my algorithm, proposed method, what values I got for horizontal correlation, vertical and diagonal correlations. As I told, always for original image, that is horizontal, vertical or diagonal, the correlation value should be close to 1 because pixels are highly correlated here if you see the neighboring pixels. But if we go with the encrypted image, it should be highly uncorrelated. Okay, the neighboring pixels should have a no correlation, like should not be correlated to each other. So you can see the value is less than 1. Can be negative or very near to 0. Okay, so that I got. Even if you see the other, like I have referred 3 paper, okay, Tang, a few, and these are the others. So if he's referred their values also, okay, they are also getting near to their range, right? Horizontal correlation value, it's fine. Okay, far better we can say, or nearby. I'm getting encrypted image correlation value, horizontal, vertical and diagonal. So now with respect to image I have done for the histogram and the correlation analysis also. So I have taken some 5 random images, which is I got from SIPA database. So SIPA database, because the images quality is good actually. So that's what I have chosen image from SIPA database. So these are the input image histograms, which will be not uniform, right? And if you go with the histogram of the encrypted image, you can see you'll be getting uniform histogram. Okay, and these are the encrypted image with SVM. With SVM, the how what is output we got. Okay, now here you can see correlation, vertical and diagonal correlation. Sorry, horizontal, vertical and diagonal correlation. So here all you can see the red dot represents the correlation of encrypted image, and the blue straight represent the correlation of the input image. Okay. Similarly, I have taken few more images, input images. So for all the images, these are the result I got: input histogram, the encryption by using SVM, histogram of the encrypted output, correlation analysis around horizontal, vertical, and diagonal. And so while doing my research, while doing my I think comprehensive Viva, I guess my one of my the faculty, they asked, why you're not going with real time images, why only database which you got SIPA or internet here. So I thought, okay, so real time images also I can try. So I have taken not from this normal image, I have tried for some one map image I have taken, one bank check I have taken, one medical image, which the patient lung image is infected by cancer. Okay, so this image I have taken. So this also had tried for encryption by using SVM. So I got histogram, input image, even SVM encryption, and even histogram, and even the similar, almost similar results I got for the correlation analysis also. So some real time images also have taken, and even some database which I got internet also taken. Okay, so these are the overall result analysis I can say now. So for what all images I have taken, so as I told Lena, these are the images I have taken. So these are the correlation coefficient value around horizontal, vertical, and diagonal, and even a USCA, unified USCA and NPCR and entropy, and even the time taken for each. Because yesterday I was asking how much time taken for every. Here I have taken nearby 23 second, 28, 29, 30, in this range the time has taken. Okay, and entropy values I'm getting near to 8 overall. NPCR near to 100%, and USCR nearby 33, 34, in that range I got. And average also I have taken here. So average also I'm getting near to the optimal value. I'm getting all the average values. So this is for the some real-time images, some military image, medical image, check, and one coin image I have taken. For those images also, then the calculation for EAC, NPCR, and entropy. So time taken is near to 20 to 24 seconds, and these are the values. With respect to the key space analysis, because that is the main thing. Always I will get the question when I'm doing presentation in my topic. What is a key space analysis? How much is your key? How whether you have, whether you're resist the brute force attack or not. So as I told, brute force attack is, this attack will tell us how strong your algorithm is, how how whether it is easy to crack your algorithm, or easily the attacker can get the key from the receiver. Oh yes, that's the center. So here I have used multiple secret key actually. As I told, input size itself you can consider as an external key, because it's not like always 56 cross 56 you can take for 5 12 cross 5 and 12. Okay, it's up to you. So that is one of my secret key. Permutation key I told, because I'm doing permutation here, so that is controlled by one secret key. Okay, and bit XOR, bit level XOR, you can take a bit XOR, bit level XOR also you can consider as an external key. Okay, and even the DNA sequence, I have taken adenine, thymine, guanine, and cytosine, 4 nitrogen bases. So for the 4 button bases, maximum 2 byte keys I have taken. Then for scrambling, Arnold scrambling, you can control your scrambling with the help of one secret key. Yes. then kernel type, then constant, then even for gamma. These three are coming under SVM. So the parameters coming in SVM. I have shown the SVM parameter, and in that these parameters are coming. So here also these values you can control, you can change it. And for different values, will get different results. You can see. So I have done so many trial and error to get the proper result. So SVM trained values, every time you won't get the proper result. So you have to change the SVM parameters based upon your input actually. So that with that trial and error, finally I got like a proper encrypted image. So as if you add all this byte, okay, we are finally I'm getting 2 raised to 144 key space, which is resistant, large enough to resist a brute force attack. Because of the brute force attack means minimum 2 raised to 100 is the target. So I'm getting more than 100, 144. So I can say my algorithm is strong enough to resist against a brute force attack. So what is the conclusion? Actually, here SVM I'm using here is SVM support vector machine based encryption scheme has been used along with DNA cryptography. And here we have used block-based encryption technique, okay, to ensure the security of our algorithm, because I'm not using to entire image. So I'm using block by block. Each block I'm encrypting with different key, right? With different key I'm using. That is another secrecy here or security here. It's like block one with another one secret key, block two another. So block so V1, V2, V3, these all the block the different secret key which we use for block V1, V2, V3, and V4. It's in our hand. That also we only can change, right? So it will be difficult for the third person or attacker to guess what kind of DNA sequence he or she has generated, right? What is the secret key used for that encryption? So this and all will show us like the how secure our algorithm is. And even we have tried both qualitative and quantity performance, okay, and we evaluated all the resistance against all the attack, differential attack and statistical attack, right? And key space shows that it is resistant against brute force attack. So this paper, this work I have published in International Journal of Cloud Computing also, just Scopus Index Journal. Okay, so now I just would like to show the result also in MATLAB. I think I have run and checked once. Once again, I'll show you. So this is the code. You can select the input image, whichever you want. I have taken Lena as a standard. So this is the input, the histogram of my input. Okay. So conventional method. So here you have to do block 1, block 2, block 3, block 4, right? So as I showed, I'm controlling the encryption by using secret key. So secret key, it's you can use binary value I used. Okay, so this is my scrambled image. Okay, scrambled image. That histogram of that first level of encryption, which is not that much uniform, right? Encrypted image and histogram both. Okay. So now we'll go for SVM training. So these are the SVM parameters. Okay. And the training still is going on. So I'm not doing any classification here. Just with this input and target, I have trained my SVM. So SVM will give a set of values from 0 to 255, which I have used as my pixel value for encryption. Right. So here I have done data hiding also just to check whether I can hide any information along with this image. So data hiding I have done here. So this is the input I have taken for data. Okay, data hiding, and this is hidden here actually. This is a result after data hiding, so it's not visible, right? So data to hide with SVM, and with the ref of SVM I can hide also. So that I have not included in my PPT, but this result is like I'm getting. So just I want to show the same thing: data hiding and encryption using SVM. Next stage is we have encrypted by using after hiding the input. Okay, I have encrypted by using SVM. So it will take nearly 20 seconds to encrypt. Yeah, done. So around 18, it took around 18 seconds. Okay, 18 seconds for encryption. So let me close other image. So you can easily, I can show. 1, 2, 3. Yeah, here is an encrypted image by using SVM. Okay, final encrypted image by using SVM and histogram with SVM. So I'm getting uniform image. Okay, now we'll go for the performance evaluation. So evaluation metrics, as I told, we have NPCR, UACI, right? All the. So here you can see the correlation coefficient analysis. Okay. So here also have given some secret key to. Yeah, here you can see all the values, correlation coefficient value, and entropy I'm getting near to 8, horizontal correlation, vertical correlation value, diagonal, and NPCR value 99.6 I'm getting, and UIC is 36.0249. And okay, with SVM, encrypted image with SVM, correlation analysis 1, 2. I think diagonal is taking little time. Horizontal, vertical, and yeah, this is the image after decryption. Okay, again, final image, the same block I got it back. Okay, before decryption, the scrambled image. So I think I have to get diagonal pixel projection. Okay, so decryption encryption over, only full performance analysis is taking time. So decryption encryption have taken less time only, as I showed already here. Okay, 18 seconds, 18.42 seconds only taken. Okay, all together. Yeah. So any doubt in this session, ma'am? Mine is over. I'm just waiting for one more image to get performance analysis diagonal. That's about this work. I hope this work will be benefit for like those who are doing research in this area. If they can have any doubt in this topic, you can ask, ma'am. Sir. Yeah. Usha, ma'am. Venkatesh, sir.
Yes, ma'am.
Yeah. Anyone is having any doubt, they can ask, ma'am.
Dear participants, is anyone willing to ask questions?
Good afternoon, ma'am. Nice
Yeah,
presentation, ma'am. I'm Manigan from Masala University, ma'am.
Yeah. Good afternoon.
Yeah, ma'am. And figure 2, ma'am.
Figure 2.
Yes, ma'am. I am from mathematical cryptography.
Yeah.
Okay, ma'am. What is the meaning of weight and bias, ma'am?
Sir, for training SVM, if
I
you go
don't know
with any
about the STM. I am
no,
mathematical.
if you go with any machine learning concept, sir, therefore we need training, testing, and validation, right? We have to do training first, then you have to test it, then you have to check the validation.
For training, we need a data set, right? Data set.
Yeah, data set. For data
So
set,
where we get the data set, ma'am?
data set actually here I'm training only with my input as 0 to 55 and encrypted output as a target. Okay, if you want, we can generate or you can get 1,000 or 100 of images from the internet also. You can train it actually. So I have my idea is just to get the encrypted image. So I don't need to train so many images here. Actually.
Okay, ma'am. That all generated data set, all are keys, right?
Yeah, that's all I'm a secret key. Yeah,
That is authenticate, ma'am, because key should be authenticate, right?
Yeah, authenticate. Yes.
If anyone changes the data set value, because that you mentioned that you can generate randomly, right?
Yeah, randomly.
So how will affect in the key changes in our model, ma'am? And also we didn't mention in your presentation, from my presentation, you just encryption only, right, ma'am?
Yeah.
What about the other part of the decryption, ma'am?
Decryption says a random key. I'm telling you, is randomly generated, but I know the secret key, right? It's not like I'm not taking the same key for decryption. Same key, I have to save the key, whatever key key I'm using here. I use in MATLAB. In this MATLAB, we have the option to save the whatever data we generated, right? So I've saved the same key I'm using for decryption actually.
Yes, ma'am. What is the meaning bias, ma'am? Bias.
Weight and bias. So, sir, if you go with any machine learning concept, sir, machine learning or ANN, we need a weight and a bias. Okay, to activate to next, because it's have a lot of neurons. Sir, neurons. We are activating the neuron with the help of weight and bias. Okay, it will do some calculation. We have an equations actually. So
Okay,
weight input image
computer
into
science.
weight. Input image
In
into
computer
weight
science.
plus bias. Yeah.
I don't know the terminology bias, ma'am. That's what I'm asking. And also,
Yeah.
we are encryption one time, and also we are encryption the same thing second time, right?
Second time, yeah. To do
Then,
like to create more complicated, like,
like
I want more secure. So I'm doing double encryption here, double 2 times. I'm doing.
like hashing algorithm.
Yeah,
Hashing.
I can't say, but this is like first level of encryption input. I'm doing one more encryption with another secret key. So so it will be difficult for the attacker to analyze to get information from the data. So I'm making it really complicated for the attacker.
Yeah, ma'am. That's only I'm asking yesterday. What is the complexity of the you mentioned the word is complexity. Yeah. So what is
Complexity.
the complexity of your problem? Based on the complexity, then only we'll say that problem is order of
Yeah,
n or log n
yes.
or log n
Yes,
square.
yes. So how much for complexity if you do
How
also?
much
Sorry.
we encrypted, how much
Okay.
we use the key, that much of memory space also is occupied, right?
Yes.
So,
So key space should be more have a measure also. You can't use big bulk key space here.
if a key bit length is very long, it will take more time to encrypt and decrypt.
Yes. But
For one time, but
yes.
from your work, you encrypt 2 times. So, what is the time complexity for your problem, ma'am?
No, so I had shown, sir, I took only 18 seconds only. See, even though I'm randomly generate DNA sequence, a secret key 1 time, 2 time, okay. It's a fraction of second happening actually. For MATLAB to generate a DNA matrix, secret key and bit XORing, and this is like a fraction of second only. What time taking is for that plotting the graph, it is taking little time actually.
Okay, ma'am.
Yes. And so bias and weight, if you see in any machine learning AI algorithm, weight input into weight plus bias, that is the equation actually. Each and every level of input is doing this calculation. Okay, then it is going to next level. So if you take an ANN means neuron, first stage of neuron is a like it has to be trained. Train the sense weight into input plus bias. Okay, that output is given to the next stage. Again, next stage to next stage. So each every stage this calculation is actually happening. So weight and bias is another secret code, secret key actually that we can control. It's in our hand. Same way reverse we can do.
Okay, ma'am.
So
Thank you, ma'am.
yeah. Sir, anything? Yes, sir.
Ma'am, and also another
Yeah.
doubt.
Yes, sir.
That DNA secret key one.
Yeah.
You mentioned B1, B2.
B1, B2, B1, B2, B3, B4. Yeah.
This is order or this is also random? B1 is
B1,
D,
B2,
B2 is
B3 is
D.
actually this one,
Why
sir.
you take
Block 1,
B4?
block 3, block 4.
Why you taking
This one.
B4 is a average of the first two. This is a random.
That is no, that you can change, because this is my algorithm. So I just taken in this way. I want to D is my input. Transpose of that matrix is another secret key. The same secret key, because same secret key I can't use for encrypting all the 4 blocks, right? So I have taken different key.
Okay,
D transpose, rotating D by 90 twice, then D plus D transpose by 2. So this we can do, sir, in different whatever your way you can do. Yeah.
B1, B2, B3 for secret key.
Yeah.
What about Q1, Q2, Q3 for? What is the
Q3
meaning of?
for this output. One block.
Oh, okay.
Okay.
Oh, block.
Yeah.
Block.
This is
Okay.
block. This either we can change the way. This is variable only, sir. Even
So for 4 block, you are creating 4 secret key, right?
yeah, 4 secret key. So that's what it is looking like. So you can see it's looking different, right? One block, one encrypted.
Okay, ma'am.
Another
I have
encrypted.
another
Yeah.
doubt.
Yeah.
So block 1, you have a DNA sequence 1.
Yes.
Block 2, you have DNA sequence 2 randomly.
Yeah.
In the same way, we can. Is it possible to generate another set of sequence DNA sequence for B3 another set of sequence for
Yeah, we can use it without using this calculation also. We can
any
generate.
any
Yeah.
relation, any conditional relation or restriction is there for setting a secret value of B1, B2, B3, B4?
Yes. We can take random rand generation is a MATLAB random permutation generation. Okay, we can use rand to generate random DNA sequence actually.
Okay, ma'am. Okay, nice presentation, ma'am. Thank you, ma'am.
Thank you, sir. Thank you. Is participants any doubt or any discussion, or Usha ma'am, Devi ma'am, shall we wind up?
Participants, do you have any questions to ask? Ma'am, I think you have encrypted their minds, it seems.
Okay.
So everyone is silent.
No.
Devi ma'am, shall we? Okay. Thank you so much ma'am, for the explicit description about the encryption algorithm using SVM technology, ma'am. The minute details and analysis you have presented clearly portray the concepts. So everyone is keenly listening, and there is no questions, it seems.
Okay. Okay.
Thank you so much, ma'am.
Thank you all. Thank you for listening.
Thank you, ma'am. Thank you.
Thank you, sir.
Thank you.
Venkatesh, sir. Venkatesh, sir, is there a photo session, sir? Shall we have a photo session, sir? Dear participants, can you please switch on the video? Dr. Devikala, ma'am. Yes, sir. Venkatesh, sir.
Yes, madam. Captured, madam. Thank you.
Yes, sir. Thank you, participants. Thank you for the good response. Very happy to see you all. Thank you, Shima, ma'am.
Thank you.
Thank you so much, ma'am.
Thank you.
Dear participants, I think tomorrow we have to join at 1 o'clock. So make yourself ready, plan accordingly to join earlier, 1 hour earlier. Thank you, participants. Thank you for the nice cooperation. Thank you.